Hello everyone. Last time I promised that we should look briefly about locally weighted regression, which I think we should, because locally weighted regression and the probability interpretation of the linear regression, those two help us, like they build us to logistic regression. So I think we should. And what is local weighted regression? Local weighted regression is a non-parametric regression method that relaxes the assumption of global linear regression. You see, if I may illustrate that here, for linear regression, for linear regression, if we have our data set, and let me illustrate that here. If we plot our data, you will excuse me for my bad handwriting, but for linear regression, if we have this kind of data set, and maybe we have illustrated it, drawn it like that, for linear regression we would fit a model, and this model is what we call a global regression relationship for this data, because it is one model for the entire data. And what would happen, let me assume we have a simple linear regression. We would have a model illustrated by this. This is beta naught plus beta 1. So we would fit this model with that format. This is being our model, right? And what happens here, we are saying we have a global linear relationship. It is one model, right? And this indicates that the model parameters, which is the betas, are constant, right? That what do we mean constant? That for whatever data set we would have, we would only remain with two model parameters, that is beta naught and beta 1, right? However big our data set could be, that would be the case. And that is linear regression analysis. So for local weighted regression, it changes a little bit. It changes a little bit. You have to excuse my bad handwriting and the drawing. So if still we have the same data set as the one we have had previously, the one I have just drawn, I think that is it. So for this kind of data set, it is the same data set, assuming the same data set, but I want you to appreciate the difference between the local weighted regression and the linear regression. So for the same data set, what the local weighted regression dictates that we choose we can't have that global linear relationship, this line, we can't have it. No, that's what it says. What it focuses on, that we choose which point do you want to predict. Let me say we want to predict a point here, we want to predict a value here, right? So for local weighted regression, it says that we focus on the local neighborhood, like we focus on the data near this value, right, on both ends. Let me say the value near this x, the x we want to predict, that we focus on that value, and therefore we choose that data, reason being that they have the maximum likelihood. So this data has the maximum likelihood. What does that mean? That this value, this value, we choose that value because the theta or the model parameter maximizes the likelihood for that value, and therefore it reduces the cost function. This is what it means. Anyway, I'm going to go into the calculation and illustrate better, but for now, that what it means that these values, each of this value is assigned a weight, and usually the values close to the one we want to predict, they have more weights, and those which are far from, like, for instance, like this one, which it is too far from here, so it has less weight. In other words, it means it has less impact on whatever to do with this x. So that's why it says that no, we shouldn't actually focus much about this kind of data, the one here, because it is too far from what we want to predict. Let us maximize the likelihood. Okay, let us take that value, that data set which is too close to here, because they have more weight. In other words, they have more impact on this. And from there, so after identifying that, then we can fit the linear regression model on only this, right? And we make prediction. That's what it means. For instance, if at all we also want to predict a value here, want to predict our value here, we would still do the same. We would only focus on the value which is close to that value by looking at, we say that looking at the local neighborhood of that value, and we fit a model here. Then we make a prediction. It could be like this. Then we make a prediction by only focusing on this data set, leaving out this other part of the data because they carry less impact to this value, or if not, even they don't carry any effect, they don't have any effect to this value. So that's what local weighted linear regression is all about. Now, therefore, each point, like these points, let me say for this case, each point, a weighted linear regression is formed. Now this is the weighted linear regression, this one, right? For each point, the one we want to predict, we only do the linear regression for that point, right? As we have done here and so here. Now that means we can't have a global, as I said here, we can't have a global linear relationship, no, but we either have, we can have multiple depending on the values we want to predict. So that simplifies the narrative which we discussed here, that these ones, the main constant for linear regression. For this case, local weighted regression, they don't remain, they be changing, right? For each point we want to predict, we would have another model parameters, right? Beta 1 and beta naught. So we will get beta naught and beta 1 depending on the value we want to predict. If it is this case, the betas will be for only this data point. Now if you want to make another prediction, let me say this one, then the beta naught and beta 1 will be for only this part or for that data set. Therefore, we can't have, that's why we say non-parametric, meaning those betas or the model parameters are not constant. They keep on changing depending on the data set or the data point we want to predict, right? So that's the biggest difference this local weighted regression introduces, that there's no that idea of global the global linear relationship is no more. For it introduces the idea that the relationship is not always global and linear, right? That's what it really says. And it shows that it shows how weights affect the regression. So that's what we have just illustrated here, that weights for the data set which are close to the point we want to predict, they actually carry more weights than the one which are far from the point we want to predict. So that is another point it introduces, that weight has more effect on the regression, which we didn't see in the linear regression. So now let us dive deep. I think we have gotten an overview of locally weighted regression. So I want us to look at the formula, how we fit it, and appreciate it more better. So we said that we fit from here. We illustrated that we only focus on here. That means the model parameters here carry more weight, right? And they maximizes the likelihood. Likelihood will mean that we take only this data which maximizes, which minimizes. For this data here, because they carry more weight, they maximizes the likelihood, right? So that means we take a theta which maximizes the likelihood. In other words, we take a theta, we take the DC values because they carry more weights. That is what the maximizing the likelihood is all about. And in return, that means they reduce the cost function, right? So that's what we say, that we fit theta that minimizes the cost function. That's all about. And the cost function for this case, it will be summation of I is equal to 1 up to m, then weight. Remember we said we attach weight for each weight I into our normal cost function as we saw it in regression, yi minus the transpose of theta, xi. We discussed the rest of this in our linear regression. This is squared. So this time around we attach weight to the cost function. So, and we are going to really look at that more, the weight thing. So this is the weight function, yeah? And the weight function weight I is equal to exponent of negative the data set or the model input minus the value we want to predict, right? The value we want to predict squared over 2 tau. This is tau squared, yeah? 2 tau squared. So anyway, this bracket is all over this. This bracket is all over that, right? So that's the weight. Here is the data set. This x represents, let me illustrate it here. This one represent the data set, right? The values here which we illustrated here, these values, that's what that x represents. And now this x, this one represents the target, what we want to predict. For instance, for this case, this one, right? So that is the weight, and that's how it is. And this is tau. Tau, it measures the bandwidth of okay, we are going to see that later, but it measures the bandwidth. We are going to see that, what that means. We're going to see what that means. And now, point to note that if x, the difference between xi, which is the data set, minus minus the target, if this value is too small, if this value is too small, in other words, it will approximate to 0, right? So meaning the weight, it will be 1 exponent of 0, right? Exponent of 0, exponent of 0. So weight I will be equal to 1. What does this mean? If this is too small, meaning, okay, if I can redraw the data set for illustration purpose. Let me say we have that, and this goes up to here. Now, and we want to predict this value. Let me call it x. If we have this value, what will this mean? We are going to get this, the data set, this value, these ones minus x, and we get the difference here, right? We get all of this. That means if this is too small, literally it indicates it is too close. This x, that data set is too close here, right? Because this value minus this one, you may find that they are completely close to each other, right? So that's why we are saying if it is too small, this will be 0, and this being, I mean, this will be 0, and the exponent of 0, it will give us 1. So that means the values here will be assigned to weight 1, right? And let us look at now another scenario. If this is too big, that means the difference between this value we want to predict and the data set is really big. For instance, it could be this here, this value minus this. The difference may be big because it is far from here. It will be here, right? It will be this side. So meaning this will be big, to be too big, and the exponent of a very big positive or big number, it will give us 0. The exponent will give us 0, and we'll have weight equals to 0, right? So meaning this is too far from here, right? And these values will send a weight of 0, meaning that's what we said earlier. It is less helpful for this case of predicting this value. That's why in most cases we neglect those and we focus on only these values with weight 1, because they are too close, and I think that's what we call maximizing the likelihood. In other words, we are reducing the cost function, right? So that's what the idea of weight is coming from, right? So now if I can illustrate more with this, how we come up with that weight, I think it will make more sense if I illustrate how we come up with that weight, still considering the same kind of data set. So if we have that kind of data set, what will happen? We will actually draw the weight, which is, as we saw, it is exponent of negative the value we want to, the data set, which is xi, minus the value we want to predict, or the target, right? Squared over 2 tau squared. So we draw this, and this will form a barrel-shaped shape, kind of like that of a normal distribution, but it's not a normal distribution. It will just make the same shape. So we will draw it here. file. Let me draw it using a different color so that you really get. So we will draw it will make that kind of shape. And what happens, the weight of this value is the height from here to that. The weight of this value is the height from here to this, and so on. Let me say we want to predict, okay, the weight of this to be the height of that, the weight of this to be the height of that, right? And so on and so on, right? And the weight of this, it will be this height, right? And so on and so on. So assuming we want to predict this value x, assuming this is the value we want to predict, right? Or the target value. You may say that the targeted value. Now, each value here, we said that height represents the weight. This represents the weight, right? So each value represents the weight. This one represents the weight. Now, how do we come up with like this shape here? How far it will go or how short it could be? That's what tau represents. So tau gives us the width of this, right? The width of this, the width of that, those values, that is tau. That is the importance of tau in this formula, right? It gives us that width or the bandwidth of that shape. Now, putting more sense to what we discussed earlier, that if this is the value we want to predict, so the difference from here, the value we want to predict, and the value which is far from that value, which will be here, assigned with this weight, it will be 0, right? The weight here, it will be 0 for those values, so that may not be important in making the prediction for this value. That's why we will come and choose. You may find all of these values, they may have weight 0 for that case, because they are far from this value we want to predict. And only these values, let me just choose like this one, since they are too close to the value we want to predict. Actually, if the value we want to predict is here instead, and is not so if the value we want to predict is here, the value we want to predict is this one instead, so we will find that only these weight, all of these values, they are the one relevant, because their weight will always be 1. For these weights, their weights will be 1, so they maximizes the likelihood. In other words, you have chosen theta, which maximizes the likelihood. In other words, it maximizes the likelihood. It chooses the data which is more relevant for the prediction of this value, and in so doing, it minimizes the cost function. It minimizes the cost function, right? That's the entire point for this. And now, since that is the case, we would now fit the regression model, and we determine, we would now fit here the regression model, beta naught plus beta 1 x, right? And we find the betas and we make the prediction only based on this data here, right? So if the value we want to predict is here, right, as let me say x, the value we want to predict that we will still do the same, because these values will have more weights. So theta for that value will carry more weight, and then we'll draw a regression here, and we find another beta, we find another model, okay, plus beta 1 x1 and so on, and so to this, right? So that's where the idea of global linear relationship is not, or it relaxes, this local weighted regression relaxes that idea of global linear regression. So that's all about the local weighted regression, unless you have another point, but I think I've exhausted it, and that is it. Thank you. So this and the probability interpretation of linear regression, which we showed earlier, they actually contribute, or they drive us to logistic regression because of the probabilities involved. And actually this should come first before the probability interpretation of linear regression, because the probability interpretation of linear regression builds on this idea. Another word, thank you. See you.